You may have seen these infinite sum visual proofs before, where by cleverly drawing shapes, you can show that the sum of infinite terms results in a finite area. I think these are cool, but was always just a little annoyed about how for each infinite summation, you need to find a new way to arrange a set of infinite shapes to show the finite result. In the background, I have the visual proof for showing that 1/2 plus 1/4 plus 1/8 and so on converges to 1. But what if I wanted to show what 1/3 plus 1/9 plus 1/27 equaled? I can't reuse any of my existing visual proof. That's when I started thinking in terms of probabilities, namely a spinner with different sections and a single simple rule. Here I have an example spinner with two sections, labeled A and B, with the rule that if the spinner lands on B, the result is discarded and the spinner is spun again. Here this is demonstrated. The first result is an A. The second spin lands on B, so the result is discarded and the spinner is spun again. Intuitively, this means that A is the only section that the spinner can land on, making it a 100% chance that each valid result will be an A. Now let's look at a spinner with 3 equally sized sections, and the rule that C results are discarded and respun. On the right are the simulated results of 1 million valid spins. Both A and B are landed on roughly 50% of the time. For a spinner with 4 equally sized sections, A, B, and C are landed on roughly 1/3 of the time. Finally, we will look at the following spinner, which empirically has A landed on half the time, B 1/6 the time, and C 1/3 the time. Let's look at these spinners using probability to see if we can determine the underlying patterns. First, let's sum all of the probabilities that A is landed on. The first way to get an A result is to land on it for the first spin, which has a chance of 1/2. The next way to get an A is if the first spin lands on B, and then the second spin lands on A. This has a 1/2 chance to land on B for the first spin, and then a 1/2 chance to land on A for the second spin, for a total chance of 1/4. The next way to get an A is to land on B twice and then A. This has a 1/8 chance. This continues on infinitely. We already know that getting A is the only possible result, so the chance of getting A must approach 1 as the number of spins increases. This diagram is a bit unwieldy, as it goes on forever. We can convert this diagram to something called a Markov chain, where each state has probabilistic transitions. From state B, we have a 1/2 chance to transition to state B, and a 1/2 chance to transition to state A. Once in state A, the result never transitions from anything but A. In this case, A is called an absorbing or terminal state. Markov chains have a transition matrix that encode the probabilities of each state transition. Here the matrix shows the probability of changing states from spin n to spin n plus 1. For example, if starting in state A, there's a 100% chance to stay in state A, and a 0% chance to transition to state B. If starting in state B, there's a 50% chance to stay in state B, and a 50% chance to transition to state A. Markov chains can also have an input distribution matrix, denoted here as bold pi. This matrix encodes the starting distribution of the states. Markov chains have a useful property where the input distribution matrix multiplied by the transition matrix raised to a power gives an output distribution matrix. For example, after one spin, there's a 3/4 chance to be in state A and a 1/4 chance to be in state B. By raising the P matrix to higher powers, we can calculate the chance of being in each state after more and more spins. As number of spins increases, the chance of ending in the A state approaches 1. Mathematically, we can see this by taking the limit of the number of spins. Let's look at a more complicated example, for a spinner with 3 states. Here we have a new Markov chain and transition matrix. We can calculate the chance of each state for the first 3 spins. Recall that each column in the output matrix is giving the chance of being in a specific state at that spin. The yellow box is around the chance for being in state A. At this point, you might be able to visually determine the closed form expression for the probability of being in state A as a function of number of spins. If you can't, we can use a linear reoccurrence relation to find the expression. If you studied electrical engineering, you might know these as difference equations. Here, I will use the reoccurrence relation of f of n equals f of n minus 1 over 3 plus 1/3. This relation is non-homogeneous, so we have to go through 3 steps to get the closed form equation. The first step is to find the homogeneous solution, which is f of n equals c1 times 1/3 to the n. The next step is to find the non-homogeneous solution. Here, we guess the equation comes in the form of a constant d times 1/3, which results in f of n equals 1/2. Finally, we get the combined solution from the homogeneous and non-homogeneous results, and can use an initial condition to solve for c1. Any of the initial conditions work. Here I use f of 0 equals 1/3. The final combined solution is f of n equals 1/2 minus 1/3 raised to the n plus 1 power. Taking the limit of f of n yields 1/2. Thus, 1/3 plus 1/9 plus 1/27 and so on converges to a value of 1/2. We can apply the same logic to the spinner with 4 quadrants, which gives a result of a new infinite summation. A fast calculation is to take the ratio of the A sector's area and the ratio of all absorbing state areas. In this case, the area of the A section is 1/3 the total valid area. Here we can nearly instantly calculate the result of 3/8 times the infinite summation of 1/4 to the n, starting at n equals 0, which is 1/2. The term inside the summation is the probability of landing on the respin sector, and the term outside the summation is the absolute size of A. The result is the ratio of the area of A to the area of all other absorbing sectors, aka valid results. The thing I like about this method is that it applies to any spinner divided into finite sections, with the rule that one of the sections results in a respin. There's no need to find specific shapes to prove other results. Workflow is exactly the same. Another thing I like about this method is how it relates probabilities, infinite sums, and reoccurrence relations. I find this is one of the joys of working on math problems. Over the course of working on a problem, you can invoke knowledge and techniques from many different disciplines. Anyway, let me know if you have any questions, and thank you for watching.